Welcome. I'm Dr. Morton, and this is the overview of Logic Design Chapter 17. Let me just explain a little bit. So one of my deep convictions for writing this book was to include material on how students can grow and learn, grow in their ability, or learn and grow in their ability to develop algorithms. It's been my observation over the last 20 years that some people kind of have a knack for it, but most students do struggle with figuring out sort of the approach to the problem and being able to codify that with, say, a written set of instructions, typically a computer program. So the last two chapters, this chapter and the last chapter, are basically focused on trying to enhance that skill and work on that skill. But I'm going to be right up front and say this is a work in progress because I'm not sure how to teach this. So I'm always welcome for any feedback, and I'm really interested to improve my ability to present this information in a way that actually does help students increase their skills in this area. With that said, let's jump into it. So, yeah, sorry. There we go. Okay, and I've just finally figured out how to make this cursor visible all the time when I'm in the book here. It's amazing. This software is great, but there's lots of little details to learn. Okay, so this is chapter 17 in the book. And you can see we have a little picture here. And notice I've got some gears that are meshing. And that's the whole idea of, we kind of have to figure out how we get from some kind of rotation here to the other rotations and speed of rotations that we need and directions. And normally our algorithms are represented in steps. And that is if it's a serial algorithm, which is pretty much how we think. One of the things that's interesting, I'll go back here. The human brain is really set up as a massive parallel device. But when you think, your brain's working in parallel, and you process some things often in parallel. But when you approach a problem, you almost always think in steps. And generally, our brains are very much operating in sort of a present tense mode where, there's a lot of stuff going on. You're controlling respiration, you're controlling heart rate, you're controlling body temperature, you're controlling metabolic rates, you're controlling muscle tone, you're monitoring how full your bladder is and how your colon's doing, and you're continually processing visual stimuli all the time. Such that if there's a sudden flash in the background or a movement that you're not actually focused on, but it will catch your attention because you're processing this. And not only that, but say you're walking. So as you're walking, you're not thinking really about every step unless you've got a pain in your foot or something. Then you might be. But mostly you walk without a lot of thought. You drive without a lot of thought in many cases. If you drive in the roads in San Antonio, you know that's true. We have some bad drivers. I might be one of them. But so you do a lot of parallel things, but you're really conscious about one thing. I mean, okay, there are people who can multitask, but for the most part, we really think in a very serial way, even though our brains are massively parallel. That's really where we get our intelligence. Our single cycle time in our brains, if you want to compare our brain, the clock in our brain, to say the clock of a computer, our brains have something like a 20 millisecond clock compared to, say, a gigahertz clock on an Intel or AMD chip. That's quite a contrast in speed. And yet, for many things, we can still outthink the computers. It is true that the chess computers now can beat any of the grandmasters, but but that's mostly because of their ability to think so far ahead and to explore so many possibilities so quickly. Anyway, so I don't want to just ramble on, but it is important to understand that we do have this interesting contrast where if we can take an algorithm and turn it from a step 1, step 2, step 3, so forth algorithm into doing all the steps at the same time, then we can increase the speed at which we can process this algorithm almost without limit, because we can add more processors. And we can do it, and we can do the steps all at the same time, potentially. But if we have to think in serial, then we're basically stuck with the fastest processor we can afford. And there are limits to how fast we can do that. This is the whole allure of quantum computing. Quantum computing holds the prospect of simultaneously exploring all possible solutions simultaneously in a massively parallel way because of quantum entanglement. And the problem with quantum computing is, of all the solutions that the quantum computer is crunching out, because when you interrogate it, you disrupt the quantum entanglement, and so it collapses to a single solution. How do you get it to collapse to the solution you're interested in is one of the real keys. The other thing is scaling. Quantum computers currently don't scale well, and so to get up to the number of qubits we really need to do important things, we have to be able to scale up, and we can't do that right now. But probably that'll be solved. The question then is still going to be how to have a generally applicable algorithm where we can choose the solution we're interested in and get it to collapse to that when we interrogate it. All right, so let me go back to the book. So here are the learning objectives. I want you to be able to write an algorithm for the solution for interfacing a push button to a microprocessor. And I want you to be able to describe 2 logical approaches to developing an algorithm for a sequence detector. Yep, you can't see it. Sorry. Okay, so write an algorithm for the push button, and be able to describe 2 logical approaches to develop an algorithm for a sequence detector. And finally, list at least 3 typical challenges when designing a user interface. So we have a little glossary here. A user interface is designed as the connection between the hardware and the user. It's implemented with hardware devices controlled by software running on a microprocessor or a programmable logic device. And what's interesting, many of you know that I'm also a physician and an OBGYN, and I did lots of gynecologic surgery, and a lot of obstetric surgery for that matter. Did a lot of C-sections, and when you do an operation, say a C-section or a hysterectomy, a lot of times the patient doesn't get to see how the scar on the uterus or the pedicles where you excise the uterus, but they do see the scar on their belly, and so a lot of times they evaluate your surgical skills based on how their scar looks. Well, when you, as an electrical engineer, design a product and you create a really fancy product, but you have a user interface that's not real good, that's what the customer actually sees. They don't see all the amazing code running inside, doing all these complicated algorithms that maybe are unique and really forward-looking, cutting edge. But they see your user interface, and if it's not elegant and easy to use and intuitive and inviting and works well and has all sorts of positive attributes, that's how they're going to judge your product. So keep that in mind. Just like a patient judges a surgeon's surgical abilities based on their scar, customers judge the quality of your product based on the user interface. And it turns out doing good user interfaces is very challenging. All right, we'll talk about displays and actuators. Displays are basically the hardware device that turns digital information into a physical signal that can be sensed with one or more of our biological senses. So image, sound, haptic sense, tactile sense, smell, taste, or some other senses. Common examples are a monitor, an LCD, speakers, lights, vibrators or buzzers, things like that. And an actuator, this is a class of devices that can act on physical objects in some mechanical way, usually involving movement, but could include heat or other effects. An electric motor is usually part of an actuator and could be controlled by an H-bridge or a stepper motor or a servo. Also, it could be a solenoid that consists of a coil with a ferrous shaft that moves a short distance that creates some kind of motion effect that's desired, or it could be could move the other way by a spring when the coil is not energized. And these are considered outputs from a digital system, whereas the displays are also outputs, whereas sensors are inputs. This is a hardware device that transduces some physical information into a signal that has become digital information to be processed by some algorithm. And that's what we're going to be talking about, the algorithm. And an algorithm is defined as the processor steps to follow in the problem-solving operation typically implemented with a combination of hardware and software. It usually includes processing signals or data from various sensors and may have both parallel and serial operations. There is usually some form of output to mechanical actuators or displayed in some useful manner, or perhaps both. All right, so since the start of mankind, humans have been developing algorithms to solve problems. When they wanted to build the pyramids, they had to figure out how to do it. And interestingly, we're still trying to. There's been a lot of debate and research invested in trying to really get a grip on exactly how they did it. Because some of those stones were very difficult to imagine that they could actually lift them to the heights they had to lift them. So every new design requires an algorithm, and often one that has to be modified or newly developed to get the task accomplished. And we can kind of do a block diagram here where we think about we have some kind of sensor. Well, we have a processor, and into the processor we have some operator input and maybe even operator feedback from the current outputs that is sent into the processor using sensors. A keyboard would be an example of a sensor. A mouse would be another one. A joystick could be another one. Buttons, individual buttons could be another way. The processor also then uses, and the sensors also could pick up many other things besides just operator feedback. It could be analog signals coming in. It could be temperature sensors, humidity sensors, pressure sensors, strain gauges, radar echoes. It could be all sorts of things. And there's also noise usually injected with the signals and in various other ways. And then the processor, after it operates on all this input, generates some outputs in form of maybe displays or maybe actuators or both. And then the performance is monitored in some way, and there's some feedback that's given back to the processor to tell how if these outputs are what's desired in when you're using the processor to control say a plant or some sort of system you want to control, then this feedback is typically automated. If it's a little more slow, if closing the loop can be done a little slower, then sometimes the operator evaluates these displays and actuator settings and inputs their feedback into the processor through various sensors. So this is kind of the block diagram and really captures what goes on with most electronic systems today. And the processor is usually it can be a microprocessor. It can be a very fancy computer system using a microcomputer chip, or maybe something even fancier than that, maybe a whole array of cores. And then it also could be executed on unique specific hardware for a particular problem in the form of a brand new integrated circuit, or it could be implemented on a field programmable gate array. So all those are possible things. All right. So there are certain characteristics of an algorithm, and this kind of lays them out. First of all, it has to be precisely describable, which means generally that it can be written in a computer language or implemented with a digital network. Secondly, it has a defined start and end, but it can be repeated in a continuous loop. That's fine. The steps of the algorithm are ordered, and they may have various branches, but the steps are ordered. And the algorithm must be able to be executed by digital logic elements or a computer, or in some manner, the algorithm has to be actionable. Okay, so we're going to talk some about sensor input and maybe a little bit about some actuators. Of course, this is a huge topic. It could cover just a tremendous range of things, and many of the things that this might cover have very potentially very complicated theory about how to use them in some of the more optimized ways. But we're going to just take a very pedestrian approach here. We're going to look at some really simple things first, and then we'll sort of scale those up a little bit. So the first thing I want to talk about is a button, or if you will, a switch. And so here's a microprocessor, and one of its output pins from one of its output ports is coming out here. And you notice we have a resistor that's connected to VDD. Now, the power that runs the processor, the positive inside, we almost always run all this on DC power. AC doesn't really work very well here. We have to rectify the AC power into DC power, and usually shift it way down, something along 5 volts or less. These days, less, usually 3.3 volts, 1.8 volts, or maybe even lower. And so that's what the processor runs on. The positive input is VDD, and the ground input is called VSS. So when we write VDD, what we're talking about is probably 5 volts, 3.3 volts, 1.8 volts, something like that. So this resistor, usually maybe something like a few thousand ohms, maybe 10,000 ohms, something like that, is pulling this line up. And then you have a switch. When the switch is closed, it pulls this pin all the way to ground, to VSS, or 0 volts. When the switch is open, the resistor pulls the pin up to, say, 5 volts, or 3.3, or whatever we're running at, to VDD. Now, we must have this resistor. If we don't put this resistor in, then what happens, this pin floats when the switch is open. And the problem with it floating, because it has a very high impedance, as you approach with your hand, you can induce an EMF on this pin, and you can actually cause the microprocessor to variously read a high or a low, depending on which way you turn your hand. So you have no assurance of what this pin will read when the switch is open if you don't put the pull-up resistor in. So we always use a pull-up resistor. Now, many microprocessors have internal pull-ups. Sometimes the internal pull-ups are too weak to really do the job of this resistor, so we still have to have it. And then sometimes the internal pull-ups are sufficient, and we can use the internal pull-ups instead of an external pull-up. So this is your basic electrical circuit. This is how it's interfaced. But what about the software? What does it take to read this input and sense a push of a button? That seems like a very, very simple thing to think about, a simple algorithm, if you will. But it turns out it's not simple at all. It's actually fairly complicated, and can be problematic. So one of the problems, so let's look at the logic or the algorithm to read this push button. Okay, so what you can do is you can wait as long as the push button's reading high, 5 volts or 3.3 volts, you wait here until it reads 0, which means it's been pushed. And then you increment a counter and then you repeat the process. Well, this looks like it should work, but actually this particular algorithm fails miserably. And I think what I'll do is give you a little example here. I'll see if I can set this up. So let me go back to the book. So basically, this approach, wait till the button reads 0, increment the counter, and do it again, that doesn't work very well because the computer is running so fast, a million instructions a second. And that's not an especially fast microprocessor. That's a modestly slow one. We have some that are 10 times or more, maybe 100 times that speed. So, or 200 times that speed. So we can't really do that. And I did put some code here, but I'm not going to go through this. So how can we modify this simple algorithm to make it a little more workable? Well, what we do now is we wait till the button reads 1, we wait till the button reads 0, and then we increment the counter, and then we repeat. We go back to waiting till the button reads 1 again. So you can do that. And if we modify the code, let's do that. I'll modify my code a little bit. So I'll go back. Let's see. I'll go back over here, and what I'm going to do, I'm going to I'm going to change this. So I'm just going to wait instead of looping this. I'm just going to do this. And let's see how I can do this. I'll just put a continue. Put a continue there, and now we'll see how that works. All right, so I'm going to download that back into my microprocessor, and then we'll go back to our little scene here, and I'm going to have to bring the thing back in. Oh, there we go. Perfect. Okay, and so I think it's done, and so now it's all set. It's ready to go. I'm going to push the button and release it. And look, I get a count of 1, and I get a little garbage because I didn't clean up my print line. Maybe I'll fix that real quick. Let's see. How come it's doing that? It's doing so I know. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Something like that. Okay, let's do that now. And we'll run it, and that should clean that up, hopefully. We'll see. Yeah, and then we'll we'll go back over here. Oh, you couldn't see me do that. Yeah, sorry. Oops. So now there was an interesting that happened there. I only pushed the button once, but I got a count of 2. All right, so that brings up my next thing. Let me reset it, and we'll do it again. Oops. Oh, let me see. It's recording. It's double counting. Well, so let's talk about that. There's a couple of things going on here. So what I'm doing now, I'm waiting till the button reads 1. I'm waiting till it reads 0, and then I'm incrementing the counter, and then I'm going back and waiting till the button reads 1, which means I have to have released the button. So here, I wait here until I push the button. I wait here as long as the button's pushed, and then when I release the button, I drop through, increment the counter, and wait here until it's pushed again. Now, it's reading 2, and well, it's because it's not resetting. It's a little bit, yeah. So when I push the button, then it stays here. When I release it, it drops through, comes back here. I don't know. I'm not sure why it's counting 2, but I do have a potential explanation. All right. So one of the problems we have now, so this looks good, but there's a little bit of a problem, and one of the problems is buttons are noisy, and it turns out that a mechanical button does something called bouncing. So when you punch it, it doesn't necessarily cleanly make and break the circuit a single time. It actually can hit the contacts a little bit. They can vibrate a little bit, and you can get several contacts. Now that wouldn't be a problem if you're just, say, ringing a mechanical bell or something, an electrical bell that takes a good fraction of a second to respond to the power. But when you have a computer reading a pin at 1 million instructions per second, that a little bounce in the button can be interpreted that you've released the button, and so you can go through this loop a couple times, and that's kind of what's going on here. And so how do we fix that? Well, now we need an additional algorithm. So let's think about that a minute. And I don't want to change that light because it's perfectly adjusted there for my little demo. So you have to think about that. So what's going on? Or what can we do to improve our algorithm? Well, we know that bouncing can be a problem. So how can we, and the bouncing could take a few milliseconds to resolve. So maybe we could put a delay in that would cause us just to wait before we check the button again, and make sure that that the bouncing's all finished. Let's try that and see what happens. So let's go back over here to let's see. We'll turn this back on, and we'll go over here. And so I'm just going to put a little delay in, and so we'll do this. We'll do this. We'll do that, and then I'm going to delay. We'll delay, say, say 25 milliseconds. All right, we'll program that in, and you can see how I did modify the code, and so. Now we'll get this all set, and we'll go over here, and now let's see if we get rid of that problem. So we'll punch it. Oh, good. Yeah, perfect. 1. No problem at all. So that little delay fixed our little bouncing problem. And sometimes the bouncing problem's not too bad, but sometimes it can be kind of bad. So you can see a simple thing like reading a push button can become a little tricky. You have a computer that's moving 100, that's executing a 1 million instructions a second, and you have a human that may be doing billions of instructions in parallel every 20 milliseconds, but your finger doesn't move that fast, and so as a result, you get this amazing result that you can get funny readings until you put in all of the pieces you need to have a robust user interface with this simple push button. All right, so hopefully you get the idea here that user interfaces in particular, but anything you do with a computer requires not just a simple algorithm, but a robust algorithm that includes all sorts of foibles and complications that you wouldn't necessarily think of to begin with. And that's why almost every code that's ever been written had bugs in it, why there's still bugs in Windows, and it occasionally will crash on you, although much less than it used to. And some of that's because we have multiple cores now, and there can be some recovery potential available instead of just going straight to a blue, to the death of blue screen. Yeah. So here's our final, let's see, sorry. Let me fix this. Turn off that and go. So here you can see the final algorithm. Wait till the button reads 1, then wait till it reads 0, increment the counter, and then wait 5 milliseconds. I think I put in 25, and then repeat. And this gives time for any bouncing to resolve. 5 might be too short, but somewhere there's a number that works. And you can find these things out by using fancy circuits and oscilloscopes and looking at your buttons. And not only that, but unfortunately, as your device ages, your buttons will get a little dirtier over time, and the bouncing will get worse. Brand new clean buttons might not bounce at all or very little, and then later on they're going to bounce like crazy. So you have to do some work and some trial and error, to basically some experimentation to determine how much delay you really need. But you can eventually work out a very robust algorithm for the button. So let's look at some other things, and here's kind of the code, but we already kind of looked at that. All right, I want to talk about some other types of interfaces we can do. Here's another one where we have a microprocessor with a pin, and here we have a potentiometer with one end tied to ground and the other end tied to power, VDD, or VDD. Let's see, I think I did that. Yeah, VDD. And then we have the pin of the microprocessor tied to the wiper that can be moved along. So when the wiper is all the way down here, it's going to read very close to 0 volts, and up here it's going to read VDD. Say that's 5 volts or 3.3 or whatever. So this is called a pot, or a potentiometer, and it's a very nice way to have an input into a processor where you can control it over a range. And the nice thing is, so how does this work in the processor? Well, inside the processor, we have to have an analog to digital converter to convert this analog voltage from ground to 5 volts into a digital value, depending on the resolution of your A to D converter. In the chip we use in Micro 1, that resolution is 10 bits. So we go from 0 to 1023, 1023. In the processor we use in Micro 2, it has a 16-bit A to D converter, and so that goes from 0 to 64K. But we can scale that 0 to 64K or that 0 to 1023 over whatever we want. So we can compress the range a little bit and fit it into, say, 1 to 10. Or we can make it 1 to 100, or whatever we want to do. We have a fair amount of control over that. And that gives us a really nice way to set thresholds and adjust values. Like if you wanted to set your thermostat, this would be a good way to do it, although a lot of people use up-down buttons. That's another way to do it. And those interfaces, some are nicer and more enjoyable for customers to use, and some are less so. And of course, again, remember the surgeon and the incision on the tummy. That's all the patient sees. So that's how they decide whether you're a good surgeon or bad surgeon, assuming they survive the case. Well, same with your user interface. That's what they see. And they may not be happy if you don't have a good user interface. All right. What about an output? Well, one of the simplest outputs we can do is to use an LED. And so how do we hook up an LED to a microprocessor? Well, in the old days, we would have had to use a bipolar junction transistor or something like that to drive the LED, and we would use the micro to drive the BJT, because the microprocessors couldn't put out very much current at all. But now, or you could have used a buffer, say. But now the microprocessor can sync or source, most of them 20 to 25 milliamps, and that's all the LED needs. So we can drive the LED directly, except we have to put in this current limiting resistor. And usually we do a little calculation on this resistor to get the brightness we want. We figure out how much current we want to go through the LED, which is essentially a diode. And that's what the D in LED stands for. And we figure out what the junction drop is, and it depends on the color of the LED. If the LED is one of the earlier ones, a green one or a red one, or maybe even a yellow one, I think, it's going to have a drop of maybe 1.2 volts or something like that. If it's a fancy one, like a white one or a blue one or maybe purple, some of those will drop 2.5 volts, maybe even almost 3 volts. So you have to change your equation, but you subtract the voltage drop from this, and that tells you how much you need to drop across your current limiting resistor, which then tells you then you can use that to calculate what the value of that resistor has to be to allow to get the right current. And say you want to drive it with 20 milliamps or 18 or 16 milliamps, that's a pretty good number. Then you can calculate the required resistance that way. All right, so that's one type of output. And now here's the interesting thing: a lot of people will look at, say, this LED output and think, well, that's not a very good output device. It's either on or off, right? Well, it turns out you can actually have different blink rates, different blink patterns. You can have a fast blink rate. You can have a short blink rate. You can have a short, long, or short, long, long, short, long, long. You can actually change colors with an RGB LED, and you can actually put out a lot of information with one LED, especially an RGB LED. You can put out a tremendous amount of information. So it can be a very effective output device, display device, if you wish, to communicate information to a user. Although if you make it too complicated, then your users may not be happy again. So you have to make sure it's robust, that it's simple to learn, and fairly intuitive and all that. All right. Okay, so let's continue. So what about some mechanical outputs? Well, one of the simplest mechanical outputs is a servo, and servos are really pretty easy to interface to microprocessors. And the way this works is that your microprocessor outputs a PWM signal. Now, a PWM signal is just where you have a pulse signal that repeats at the pulse repetition frequency, and you choose that depending on what you're driving. In the case of a servo, you need to choose that period to be about 20 milliseconds, or a frequency of about 50 hertz. And then you change the time during that period, that 20 millisecond period, that your output is high, and then the rest of the time it's low, and you represent that. We call that the duty cycle, and you represent that as a percent. So we could do some examples with that, but I think I'm just gonna do a couple of drawings and try and make this so it's comprehensible here. So let me see if I can explain this a little bit. So this PWM signal, first of all, we have a pulse repetition rate. So there's normally we have this is, say, our 20 milliseconds, and then we have another 20 milliseconds, and then we have another 20 milliseconds, and so forth. And during this time, our signal, say, starts off high, and then it stays high for some part of this 20 milliseconds. So if it stays high, say, for half the time, so it's high, and then it's low, and then it starts over again, and it's high, and then it's low, and then it does it again, high and low, and so forth. When we look at this, and I didn't do a very good job, I made this too fat here, but basically I tried to draw it so about 50% of the pulse period it was high, and 50% it's low, and we call that a duty cycle that equals 50%. And we always express duty cycle in percent. So this is a 50% duty cycle. It turns out for servos that the only really important part are when we want the servo to be full one direction, we have a duty cycle that's at 1 millisecond or 5%. And when we want it to be fully extended, yes, 1/20th, right. And then when we want it to be fully the other direction, we make it 10% or 2 milliseconds. So that would be something like here, 2 milliseconds. This would be 1 millisecond. And of course that would be, instead of 50%, that would be a 10% duty cycle. All right. And when we want it to be straight, if you will, then we would make that 1.5 milliseconds, or a duty cycle of 7.5%. So this does decrease the precision that we can control the servo, depending on how many bits of resolution we have in our PWM signal. That PWM signal then has this pulse width to voltage conversion module that sends a voltage to the comparator. Then we have a little DC motor, at least for hobby servo we do. For big industrial servos, we might have a 3-phase, very powerful motor. And that motor is driving a gearbox to get us so that the shaft is turning slower and also with more power, more torque. And we have a potentiometer on the shaft, and basically we allow that that shaft to rotate something like 90 degrees. So maybe it's full, I guess that would be clockwise. Yeah, versus full counterclockwise. So it goes. I can't really do it with my arm. So it would be go full clockwise to full counterclockwise, and at one point at the 1.5 milliseconds or the 7.5% duty cycle, it would be straight up. And usually they get 180 degrees of movement, 90 one way, 90 the other way. And 90 one way is 5% duty cycle, 90 the other way is 10%, and halfway in between is 7.5. So that's how a servo works. And what happens is the pot comes down and gives the comparator a voltage that tells where the shaft is. And then the comparator, if there's a difference between the commanded position based on this voltage and the measured position based on the pot, on the shaft, then the comparator sends a signal to the motor to drive it forward or backward to change the shaft's position. And so that works pretty well. Okay. So let's see. So let's go back. The last thing, and I generally recommend doing this as a little in-class group exercise, but we take say a toaster oven, and we talk about what the requirements are. So how would we develop an algorithm to run a toaster oven? What are all the functions we need, and how would that algorithm be developed? And that might look something like this. So we'd start with the requirements. First step is to describe all the required functions. So in this case, I listed 8. Control the heating coils, both above and below the food rack. Sense the temperature in the oven. Provide a timing function to turn the oven off after a defined period of time. Provide a metal enclosure for safety, with a door and a base and a control panel. Sometimes the base drops out so you can clean all the crumbs out. Has a microprocessor that can read the temperature sensor inside the oven. turn the coils on and off to maintain a perfect temperature, and also control a user interface where you can set time. You can either do toast with the elements on both top and bottom, or you can run it at lower temperatures and just heat it up maybe, but for a defined amount of time, as opposed to say, well, I guess toasting's a defined amount of time too, but maybe a much longer time, like several minutes, and instead of just maybe 90 seconds or something. You have to provide a power cord, and then you have to provide a way to get some of that power down to 5 volts or 3.3 volts, whatever your logic's running at. And then you might want to add some spiffy details, like a little countdown timer that shows when your toast is going to be done. Or if you're using it as a little oven, you can set it for a certain amount of time to bake something at a given temperature, and you could set the temperature, you could set the time, or whatever. And then, in a robust user interface, so the user can adjust the type of use between toasting and baking, between controlling the amount of time the oven runs or the amount of toasting, and it should be intuitive, not requiring training or minimal training, and be compelling and enjoyable to use. Then the next step would be to maybe come up with a block diagram for how it would work, and then maybe begin with create a state machine that provides states for all the various functionality and how to make those work with time and temperature measurements, and obviously maybe some safety features built in, so when the doors open that you turn off the heating elements and that kind of thing, and then maybe monitoring the temperature so to never exceed a maximum temperature for the oven in case there's a malfunction, provide some backup, and then then you can come up with the components that are needed, or the functional modules, the components required, the algorithm, and all the various algorithms actually, and then you can make a test article and start to exercise your code, make sure it's going to work correctly, and then iterate that by making adjustments to your code, making adjustments to the hardware, until you get a robust, compelling, and enjoyable product to use that's safe and very functional. All right. So anyway, that's pretty much what I wanted to cover, and I just wanted you to be thinking about these things. We're going to come back and talk about some more of these issues in Chapter 18. So we'll see you in the final chapter, and maybe in a week or so, or maybe in a few days.